Hello everyone, Namaste. I am Ramnath who would like to present you the series on key learnings from chip development part 13, which is on synthesis of RTL design. This is a continuation of the earlier part 12. In this presentation, some information is provided on when synthesis stops inferring, especially related to the memory inferencing. We will also know some more details on memory features, internals, and design integration details. Here only preliminary details are given. For more details, please visit the references and other related material available on the net. Thanks for learning along with me. As described in this diagram, the RTL is fed to the synthesis along with the IPs and associated design constraints, and then it will be the RTL design will be elaborated, technology mapping and design rule checking is done, and logic optimization is done. This is as we have discussed earlier in the other parts, and then here the RTL will be converted into technology specific gates, and here as you observe the memories which are the key items, they will not be converted, be synthesized as per the RTL requirement. They will be instantiated in the gate level design of the chip. So we will figure out why it is done like that. So we need to know what are the internals of memory and how it works and all that. That is when we will be able to appreciate why the RTL content will not be inferenced even though the memories are available. That means like technology specific memories are available, synthesis will not infer them. We will find more details on why memory is not inferred as part of the synthesis. Memory is an electronic storage space where a computer chip keeps the instructions and data it needs to access quickly, so that bootloading kind of activities or any applications run smoothly due to this. Before going into the memory functioning and its inferencing topic, let us look into some aspects of the human brain, as it also contains human lot of memory. So if you see, the human brain is a complex biological system which sparks curiosity about its capacity for storing information. And if you see, actually, the brain's storage capacity is close to 10 to 100 terabytes, which is equivalent to 40 years of HD video. And the brain usually contains 86 billion neurons and 100 to 500 billion synapses. We'll come to know what are these things. However, here I want to mention that the brain can contain 14 years of HD video. That will like to see the amount of dynamic storage it contains. Actually, the content, dynamic content is not very similar to our hard drive where the capacity is constant. Here, the size matters and size varies, and it has both static memory and dynamic memory. Okay, if something is not used for a long time, it will slowly remove it. Okay, that's how it will keep on managing the capacity. Okay, memory is the building block of the brain and it can help us save. Okay, actually assume that we have seen some uh, red hot filament. Okay, especially some stoves or some hot element which some people use it to heat water and all, or some fire in the kettle. So all these things if you see, uh, immediately we will know that this is this item we should not touch. Okay, so those kind of things, it is some of these are hard coded either genetically or some we will learn over time. So all these things are stored in the memory, and these things will come into our usage very efficiently at the right time and in a quick span of time. Okay, understanding this involves hence not just a sheer volume of data within the brain, but also how the brain processes and retains it. This is very crucial, and several scientific investigations reveal a sophisticated system that far exceeds simple comparisons to digital storage device or the CPU. Okay, so that means like I am mixing here the data storage and the processing here, because there are some synapses which function in different manner. That means like neurons and all. So there are motor neurons and different types of neurons also exist. So currently I will restrict it to simple neurons, so that the understanding will be easier. Okay, so memory is an electronic storage space where a computer chip keeps the instructions and data it needs to access quickly. Thus, it helps in bootloading of computer chips, and in some cases, it facilitates many applications to run smoothly on our smartphones, computer chips, and IoT devices, etc. Before going into the memory functioning and its inferencing topic, let us look into some aspects of our human brain, as it also contains memory. The human brain, which is a complex biological system which sparks curiosity about its capacity for storing information. Brain storage capacity is close to 10 to 100 terabytes, which is equivalent to 14 years of high definition videos. And the brain contains 86 billion neurons. Here in this picture, we have shown different neurons here. These are all neurons here, like that. And it contains 86 billion neurons, brain, and it also means it contains 100 to 500 trillion synapses. Each synapse can store more than a simple on or off switch. So potentially, which means holding 4.1 to 4.7 bits per synapse. So the brain's actual usable capacity is dynamic. It is not static like our usual digital hard drive or our memory stick. Memory is one of the building blocks of the brain which keeps us safe actually. So assume we want to assume a predator sees this kind of frog. Okay, this is a poisonous frog, which it is mentioning it through its type of stripes and color. Then so many birds and snakes and other predators will avoid this one. Okay, so this is one thing, and even in our case also, sometimes if we see a snake or a tiger or something, immediately we will avoid it. Okay, so these kind of things are actually stored in our uh, brain, which will come into handy very quickly and helps us and keep us safe. Understanding this involves not just sheer volume of data, but also how the brain processes and retains the data. Actually, many scientific investigations reveal a sophisticated system exists that far exceeds simple comparisons to digital storage devices. The human brain receives signals from the body's sensory organs, gnanendriyas, and outputs information to the muscles, i.e., motor organs, karmendriyas. So, neurons communicate with each other through synapses, which are specialized junctions that allow for the transmission of signals. So, if you see here, this is the neuron structure. Here, this is the nucleus of the neuron, and these are all dendrites. There can be more dendrites than this. and there will be only one axon, and here these are the axon terminals, each one of them. And if you see here in this picture, you will know that the blue color belongs to one neuron and the yellow can belong to more than one neuron. So here if you see, the pink is also another neuron. Okay, so and it can be many neurons also. So if you see here, the neuron here, the neuron axon terminals are connected to another neuron dendrite through a synapse. So this part is called synapse. So, and here from the other neuron, their axon terminals are connected to this dendrite. Here, this blue one is dendrite, and this yellow belongs to one neuron. This yellow item belongs to another neuron, or the previous neuron, like that. So here, this part is called synapse, where they are axon terminals of one neuron is connected to dendrite of this neuron. Similarly here. So that is how the connections are formed from one neuron to another neuron. That is how the billions of neurons and trillions of synapses are existing in the brain. So the neuron communicates with each other through these synapses. So let me share a few facts about the brain. So there are 1,000 times more connections in the brain than the stars in the Milky Way galaxy. And another fact is humans use all of the brain all of the time, not just 10% of the time as we usually mention. Another fact is the human brain can consume 23 watts around of electrical power, even though it is 2% of its body weight. So see the amount of power consumption. That is why sometimes, no, when we have performed some hectic task, we will get more and more tired. Okay, so let me bring out one scenario wherein we are imagining about the first day in our school. So then we will be say we will be knowing that each time you remember such kind of old memory, then what is happening is like we are reactivating patterns of electrical and chemical activity that have been shaped, modified, and stored inside our complex brain through several network of neurons. So the process is not like retrieving a file from a computer. Usually in a computer, say if you want a specific data, we will go to a certain memory and we will ask for that data. So it is not like that. It is not just as simple as that. It is more triggering different brain regions join in at precisely the right moments. Okay, which are which by which weaving together the sensory, emotional, and factual threads that make a memory come alive. Because say assume that we have seen some item, then the visual related data should be stored and retrieved, and assume we have talked at that time in that school, first day school, then that audio related signal should be brought out. Similarly, some of the emotional related data, that will be like how did we fear on the first day, or did we play, or did we talk with our best friend, like that. All those things, these data are kept in multiple locations, okay, in the hippocampus, and that data will be retrieved. So that is why it will be triggering several network of neurons, and that whole thing will be brought back as a pleasant, either some sad or a happy or surprise moment. So that is why it basically it involves several neurons. It is not that is why it should not be compared through a computer chip, where it simply goes and fetches some data from the memory. So what I also want to mention is like the physical basis of memory lies in changes to the connections between neurons. That is what some neuroscientists say, and it is called synaptic uh, plasticity. Okay. Another fact I want to share is like our neural capacity is not infinite, and the ability to forget irrelevant or outdated information is as important as remembering what matters. That is why when we sleep, uh, during the REM sleep and all, it will be assorting the data in such a way that it will figure out whether it needs to share the short-term memory to long-term memory. All that it will be removing some data which has not been used for a long time. That is why some people during Alzheimer's disease and all, they will remember the old data because it has been fetched many times. So that neuron to neuron connections are stronger, hence they will be still be able to figure out. That is why first in, last out. Okay, and another fact is memories fade when the synaptic connections that support them weaken over time. Okay, that is what will be seen in the Alzheimer's people. Okay, so that is why we need to keep on refreshing the data as and when possible, so that our brain will be active. I will also share one more uh, information about how the information passes from one neuron to another. Okay, so assume that this neuron colored in blue wants to share information with another neuron. Uh, so here it is the dendrite is here. These are the axon, and axon terminals are here. So if you see how they will share the information, we will just briefly discuss through this picture. Okay. So if you see here, there is initially, if you see, there will be minus 70 millivolts around voltage exists. Hence, this is the resting period, and during the resting period here, the signal will not pass to the another neuron here, but when the positive ions are pumped into this nuclear neuron, then what happens is like the voltage starts to build, and it reaches from minus 70 to minus 50 millivolts and all the way up to plus 30 millivolts. When that happens, the positive ions trickle from one axon element to another, and then it will come all the way up to this axon terminal. So for example, here it will come all the way up to this axon terminal, then it will cross the small empty space. It will be in few nanometers. So that distance it will jump and then move to the another uh, dendrite of the another neuron. That is how the signal moves from one neuron to another. Okay, from here to all the way to the next neuron. So this is how they have figured out, and there are very good pictures also about how all these things happen, and this also is a great information about what is the voltage levels and all that. That is how we can say that this activity means some power consumption by the brain. And this working memory capacity of the brain is uh, kind of like unlimited, and it typically able to hold about 4 to 7 items at a time. So it is essential for reasoning, decision making, and learning, acting as a bridge between perception and long-term storage. Okay, one more fact I want to share with you. So short-term memory lasts for just 20 to 30 seconds. So, for example, when we are reading out the OTP and entering in one location, uh, once we do that one, the OTP number will fade. Okay, and we also need to know that there is no need to store that OTP information in our brain because it is more unnecessary data, as you know. So that is a part of the short-term memory. So, yeah, but if it is a long-term memory, then it will be many times, it will be rehearsed again and again. Then it will recognize that the, this is very important because that neural connection will be considered, triggered many times. As soon as it triggered many times, this gets strengthened. When it's strengthened, that becomes a strong connection. So that is how sometimes our important numbers or phone numbers of a specific individuals or our any date of birth or some things we keep on mm, coming back. That's why we remember them very quickly. And this is how the memory of the brain behaves, and it stores the information and retrieves the information because the data is kept in different forms. As you know, storing and managing data can be realized as standalone memory chips or as individual memory chip devices in a soft design of a chip. Different types of memory devices exist with the varying features to suit to different applications. The main channel for communication between uh, processor and memory is these three buses. So if you see here between processor and the memory, the control line will be initiated first, and then it will tell whether the data needs to be read from memory or to be written in memory. Assume that you want to read a data from memory, then a read signal will be propagated from the processor so to the memory. Then it needs to know which address data needs to be read. So a processor again sets like these are the address lines and so and so address bits which from which we need to get the data. Then that data will be fetched and then put onto the data bus, and it will be reached at the processor. Now assume you want to write the data onto the memory, then processor first sends a write signal onto the memory. Then it should also tell like where it needs to be written. So it needs to send the address signal through the address bus, and then it will send the associated data. It can be more than one bit. So based on the address lines from which to which it needs to be written, then it will be written properly. Okay, so uh, uh, these address lines can be 8-bit or 32-bit like that based on this memory capacity, and at so and so address line this data will be sent. So this is how the memory data will be written or retrieved by the processor. Okay, and this memory can be external to the processor or within the chip. This whole memory element can reside along with the processor. So if you see the oldest SRAM chip which is written, which is made is in 1969. That is the Intel 3101. and it is just a 64-bit bipolar SRAM. This is one more reason why uh, Microsoft Bill Gates at that time was telling that we don't need more than a few kilobytes of data on the chip. Okay, now if you see the amount of data memory we are putting is so high in GB and all. So coming back, I also want to mention now that Intel has moved to 14 angstrom, and this is used using the ribbon FinFET technology, which is made using the gate-all-around design. Okay, that is how the densest and the fastest memory access is happening. Before knowing which all memories are used in chips, let us find out what type of memories do we use in day-to-day life. Okay, so if you see, we use scratchpad. Okay, it can be a rough notebook or sometimes on the mobile phone also we use some information. uh, these kind of things we use, and here if you observe carefully, the data on the scratchpad is mainly for very short information, and it is also mainly for to get quickly convey some information so that we can execute things. Okay, and aside to that, we also use rule books. Okay, so that means like some specific standard books. Maybe it can be logarithmic tables in the olden days, or some design specifications, or some say design data information. Okay, so design guidelines, so technology rules, like that. So these things uh, will not be changing in general. Okay, so those books we use mainly for reference purpose, and we also use several material books and maps and so much of other data which we keep it we refer them in the library. So if you see, these three material or will store data, and it will also give some specific instructions on what to do and how to do. So these are the usually daily life memory elements which we use. Okay, and this way I just wanted to connect different memories we use in the chip context. So if you see in the chip context, the memory is mainly divided into two types. One is primary memory and another is secondary memory. Let us know more about the primary memory. In the primary memory, there are two types. One is SRAM, meaning static RAM. Another is dynamic RAM. In the static RAM, it is made with the transistors, and this data in this SRAM will vanish when you switch off the power. And in the case of dynamic RAM, which is made with capacitors, even though the power exists, it will be slowly leaking because capacitors slowly discharge. Okay, but in the case of SRAM, the transistors are grouped in such a way that the charge will be replenished. Okay, we'll come to that more. So there is one more type of memory which is called ROM. So this one does not lose data uh, which is stored in it, even though the power supply is switched off. So sometimes, no, in the chip boot logic purpose, or sometimes if you want to store some specific information which is used by the chip, which does not be overwritten, need not be overwritten, or does not change, that kind of information you can put it into ROM. So because of this information which is put in the chip, uh, which during the boot logic invocation, that will be read, and the chip is brought to a known state. Thus the ROM acts very helpful and in an effective manner. Aside to these, let us investigate the secondary memory. So in the case of secondary memory, this data will be will contain large amount of data it will store, and very similar to the data which exists either in SRAM, DRAM or ROM. However, the time it takes to access will be long. For example, in the case of a magnetic tape, the same data exists, and this will usually exist as an external to the chip. Because of this reason, uh, there are one advantage and disadvantage. Advantage is it can store large amount of data like a library. However, the time taken to access it or write it, it will take long time. And there are other types of data which will do the same purpose, and it is basically sometimes based on the advanced technology and all. So this may contain more data, and access times are reduced. Okay, so these are the things, and flash memory also is a very good concept, wherein by the based on the uh, mm, activation of the voltage, high voltage usually, the data can be changed or overwritten. So this will be very useful in some applications, wherein if we send some data to some chips which is having the flash memory to the customers, then they can change the data as per their need, and hence make the chip operate in different configurations. Briefly, let us discuss the different types of memories used in the chip. Okay, here if you see, this is a ROM, and here it has 9-bit address. Hence it is 512 different address lines it has, and the data is kept in that. Okay, and it can be accessed through 8 data bus. So it is mentioned as 512 by 8. Okay, and these are different chip select pins based on which this memory can be kept in different modes, in the sense like the uh, switch off mode, completely shut off, or deep sleep mode, or sleep mode, like that different modes it can be kept so that power can be saved. Aside to that, there is one more type, it is RAM. Earlier one was ROM, this is RAM. Here, since it is RAM, so you can write also onto it, aside to reading. In the ROM, it is only reading possible. So if you see here, this is the input data which has 8-bit, that's what it is having, and it is address is 16. Okay, so it is 2 into 10, 2 to the power of 16. So it is 2 to the power of 10 into 2 to the power of 6. That is why it is 64K. Different address lines exist. So within that, you can keep that, like 16 address lines exist, and within that, 64K array exists. In that, different bits can be stored. Okay, and it has the 8 output data bus. Okay, and similarly, the chip select will control whether the RAM has to be on or off, and it has a control pin by which it can perform either read or write actions. Okay, and you will just extend it little bit further. So here if you observe, this is a black block diagram of a typical SRAM whatever we have analyzed here. So here it is 256K by 16. Based on that, the number of address bits has to be 16. That means like 2 to the power of 10 into 2 to the power of 6. So 256K. So 16 address lines have to be made, and these have to be decoder multiplex so that you will be able to uh, access 256K address lines. And since it is 16 data bus, so 8 plus 8. So here it is just kept like it is a upper array and lower array. So however, these number of total number is same as here. And aside to that, there are some control signals here. As mentioned earlier, chip select, write, enable, and all. So these are all other functions. I am not going too much into it. So now if you see, these are the control bits on them. That is how address lines, data lines, and read write control signal. With that, this SRAM can be integrated into the chip with other elements. You mean to say either CPU or other DSP or some other microcontrollers like that. Let me quickly explain the internals of the SRAM. Okay, so if you see here, these are the address decoder for the rows and the column, and here since it is OR inputs of the address, hence it is 2 to the power of OR columns, and here it is Q inputs, hence it has 2 to the power of Q rows. So that is how the different number of memory elements can be accessed using Q inputs plus R inputs of the address. And this small element or this one can be represented in this manner, and there are different variations of this. Okay, and in the simplest form it looks in this manner. Okay, so here it is the word line, and this bit line and this one here it is bit line bar opposite of bit line. So here assume we want to perform a read access, then word line is activated as before, that because it has to know which element it is accessing. So based on these inputs, so and so specific memory element will be activated. So this word line is activated, then whatever data is there here will go through this one to the actual output of the memory unit, where the it is sent to the data bus. Okay, from data bus it will be connected at the processor. However, if you want to write onto this memory element, then so and so address lines will be activated, and the control signal will mention that it is a write operation. Then what happens is like the as usual address line will be activated, so that we will know which exact element will be activating, will be triggered, and this bit line they will send so and so specific information, either logic 1 or logic 0, and because this uh, mm, MOS transistor is on because of the word line activation, then the data will go through this. So once this data exists here, it will be keep on latching even though the bit line does not keep the same data all through. So it will be keep on holding the data. That is why as long as the power exists for these inverters, which are acting like a latch, then even though the word line is off and the bit line is off, that means like the MOS transistors do not function, they will be keep on storing that logic well. Now that we have understood different types of memories and how they function and why they are needed and what type of controls they exist, all these things briefly, of course, then that is one reason synthesis tool, considering all these possibilities in the sense like what type of memory, primary memory, secondary memory, in that primary memory whether it is SRAM, DRAM or ROM, like that different possibilities, and selecting the right configuration and size, that means like how many address bits, how many data bus bits it needs to select. So all these things are not easy, and sometimes what happens is like the the control bits need to be different for different situations. Those things are also not easy by the synthesis tool, because it cannot arbitrarily select which may be disadvantageous for a system performance. Aside to that, power grid compatibility. How many memory power grid exists? What are the different types of metal layers exists on the memory, and how what are the top level metal layers which are available? Based on that, different memory selections. These things and all are completely out of scope. Okay, and the operating conditions which are selective, in the sense like sometimes the same memory configuration means same number of address bit and data bit, but some memories operate at low voltages, some memories need to operate at high frequency. Based on all those things, the synthesis tool will not be able to select the right memory. Because of all these reasons, it is not easy to select the required memory and the specific configuration for the chip to work efficiently.